record this one first. Thank you so much. All right. So good morning again. Almost forgot. All right. So what we are going to have for you today is the continuation from what we did last time regarding heat. All right. And we're going to do a little bit of calculation today just to revise what we did last time. And we are going to move on to some other stuff. And I think eventually toward the end of today's lecture, you will have a chance to see what is the first law of thermodynamics is about. All right, so we're getting there, almost there. All right, so what we have for you is this problem right here. I don't know, have you tried this one before or have you tried it since last time? But if not, that's okay. We're going to go through this one together. So once again, let's go through the problem. It's a simple scenario. You're mixing the ice and water, and then the question is, what is the final temperature of the mixture? Yeah, as simple as that. But we discussed last time that this is just a problem that's talking about the heat transfer or the flow of energy from hot to cold. And we already discussed that the amount of heat that flow out from the hot part must be the same as the heat that flow into the cold part. So you can name the one that's coming from the hot, like Q hot, and the one that get into the cold part to be Q cold. Okay, that's no big deal.
Okay.
All right. And then what you have over here for you is just equate that. So from what we had last time, I was just saying that the amount of heat flow must be the same, but then we say amount, we put the absolute sign here. Sounds good? Okay. And if you would like to take into account the sign, you can sort of write this equation like Q hot equal to negative of Q cold. I will take this chance to clarify what I am saying over here, or what's the similarity or what's the difference between these two expressions. Sounds good? All right, so let's dive into it. So what we are going to do right now is just looking at the mixture over here. You have ice and you have water. Water is warmer. Ice is definitely cooler. So what you think is you assume that at the end, your final temperature will be somewhere in between 0 and 50. So let's assume this is X at X degrees Celsius somewhere. So that means you have just two sides of the story. One is about ice and the other one is about the warm water. Cool? All right, so you can imagine this. So let me start from ice. So if you have an ice here is at 0 degrees Celsius, first it has to get sort of like change the phase first. It has to melt first. Sounds good? So that means this ice eventually going to have to melt into liquid water at 0 degree first. And we already learned last time that this process take amount of heat according to the expression of mL. M is just the mass of the ice, and L is just the latent heat of solidification or fusion, okay, for this process. Cool? And then once you're done with this, the liquid water at 0 degree will start to warm up to X degrees Celsius. So it's going to get hotter, eventually going to reach X degrees Celsius. This is in the cold part. This is what's happening. And then you can just take a look at this and compare to the other part. You have water in your container starting at 50 degrees Celsius, and eventually it's going to cool down to X. So it means you can think of this one is come back here and you're going to end up with exact same liquid water, but now staying at X degrees Celsius. Sounds cool? All right. And during these two processes, these last two over here, it's just the temperature change due to the heat flow. So the expression that you're going to use is going to be Q equal to MC delta T on both of this one. All right. And what you are seeing over here is you have to equate the heat during these two sides of the process, the one that is flowing in, the one that's flowing out. You guys are, I don't know if this diagram helps or not, but this diagram just showcases that the heat involved in this process, there are two sides. This one side over here, this is the heat that flow in to warm the ice up to X degrees Celsius. And where does this heat come from? It has to come from the hot part over here. Does that make sense? All right, and that's it. So you can write down the equation So you just say, okay, come down here. You say Q. Oops, sorry, you don't need the Q anymore. So you just say M of the ice times L, the latent heat of fusion, plus, and then you follow with this M of ice, C of, now it's just water. So it's C water, regular water, and then delta T. Now you're going from 0 degree to X degree Celsius. Here's the key. So are you going to use X minus 0 for sure, right? Because temperature is increasing. So you just put X minus 0. Perfect. This is fine. So this is the total amount of heat that this ice received from the warm water. This amount of heat must be equal to, now you look at this part over here, the heat that flow out from the warm water. So it's going to be M water, C of water, and then delta T. Now here's the kicker over here. So what should we put in here, guys? Of course, it has to be delta T at that. But look at this one. The final temperature of water in the container is X. The initial water is 50. So this is initial. And this is final. So if we stick with the rule that we were talking about, the delta, the change has to be final minus initial. So if you stick with that, it has to be final minus initial. You guys with me here? Okay.
Okay.
But, so if you want to take this perfect definition of delta in here, you are guaranteed that this term is going to be negative. You guys seeing this? Because we already saw that X has to be smaller than 50. And this is the reason why if you're going to use perfect definition of the delta, you need the negative sign in the front. And that's why you following this expression right here. Does that make sense?
Okay.
Cool. All right. Okay, very cool. On the other hand, some of you will just say, well, John, I kind of know it. I kind of know that the temperature change is going from 50 to X. So as I mean, the temperature is reducing. So if we only care about the amount of heat, I can just say, I'm just going to equate to, let me use a different color over here. Let me use blue. It's an M of water, C of water. Oh, sorry, it's a small c. C of water. And then I just put 50 minus X because I know this is definitely going to be positive for me. Is that cool? All right. So if you're following the bottom expression over here, that means you already use the absolute expression for that equilibrium between the heat flow in and heat flowing out, sort of. Okay. So I hope you guys sort of like seeing just, I mean, they are similar actually. It's just the way that you want to express them mathematically. And it just depends on how you would like to approach your calculation. That's all. Okay. So don't forget, if you stick with the like a full definition of delta, you really need the negative sign because you have been taken care of the direction of the heat flow. Cool. Heat flow out and heat flow in. So there must be one that is positive and there's one that's negative. So that's why to make them equal, you need a negative sign in the front. On the other hand, if you already taken care of all the sign, you make sure that all the terms are all positive. You just say, you just use the absolute expression here. All right, guys. So that's cool.
Okay.
Alrighty. All right. That's, I hope that's pretty much to like conclude the things that I mean that's supposed to be here, I guess. Nice. Okay. And then the rest, okay, just figure out what should be X and then you are done. You guys hear the sound effect here? Wow. All right, okay. All right. Okay. Okay. Any questions so far? All right. I want you guys to try this. All right. I don't think I'm going to dive any further because there is a little bit of like a funny business going on with this kind of problem. And I hope that you'll have a chance to try this one. And you might come up with some conclusion or some questions in the future. And, you know, I have a couple of exercises in the homework. All right. So I already posted the homework. So you can check that out. The homework is in the homework area in the Google Classroom. All right. And I have decided to post the homework along with the answer.
No. Okay.
So the answer is already there. So you might be wondering, well, Ajahn, what kind of homework is this? You already give us the answer. So what kind of things that I have to hand in for the assignments? And then you just take a look at the assignments. My question will be super simple. That's, as I said, the only thing that I'm asking you guys for the assignments is just submit your work. That's all. That's all I'm asking. All right. Because the purpose of homework is just for you to practice, doing some problems and solving things, because homework sort of like give you a lot of time to solve. So it might be more complicated than the question that will show up in the exam. So if you try those homeworks, you can think of those to be like your upper limit of difficulty levels that you will face in your final exam or in any exams. All right. So it's a good sort of like representative of the worst thing that could happen in the exam. All right. So please try those homework questions. All right. And you will be surprised what kind of assignments that you are getting. It's like, are you serious? Is that easy to get like 1 point from each homework assignment? And the answer is yes. Is that easy? Okay. All right, guys. So very cool. That's what we're trying to do here. Okay, let's move on to the next one. So what we have for you next is the last question regarding the heat, okay, and the MC delta T stuff. I think I like this one a lot because it gives you the sort of like the connections between dynamics or Newtonian physics that you learned from physics 1 or from high school physics. And on top of that, a little bit of heat flow, okay, some temperature aspect of material. So let's take a look at this. You have 3-gram lead bullets at 30 degrees Celsius, and it fires at a speed of 240 meters per second into a large block of ice. All right. So you just shoot a bullet here, bam. And then in which it becomes embedded. So it's stuck in here. Okay. And you shoot it in 3 gram. Okay. 30 degrees Celsius. And the speed is 240 meters per second. All right. So when it's stuck in there, of course, you guys know that eventually there will be no speed or no velocity whatsoever. The question asked is just what quantity of ice melts. They're going to melt some ice around it. Say you see the difference between this problem and the problem that you saw before. Of course, back in the Newtonian days, you never have to deal with the temperature of the bullets, right? Does that make sense? Right? Because it's like, okay, I'm going to shoot it. I mean, this might show up in the question about maybe like momentum, for example. If you want to know what is like the momentum that gets transferred to the ice block on and on, or if the block is allowed to move, then you might have to calculate what is the final velocity of the bullet and the block that sort of like gets pushed back a little bit on and on. But this is not the problem here. The problem that we are looking here is just the block is sort of like pretty much it's fixed in place, but the bullet is being shot into this block and it's stuck in there. And the question is, what happened to the ice? See, you see the difference between what you did before and here, right? We have thermal aspect of the problem built into this kind of question. Okay, so let's take a look. So what we have over here is you want to know how much ice is going to melt. All you need to know is you just have to know how much energy is lost during this process. Does that make sense? Yeah. Okay.
Okay.
So if you know the energy before and the energy after, the disappearing of that energy must turn into the heat that eventually going to use to melt the ice. Cool. Okay. That's easy it is. So what I'm asking you to figure out is what is the initial energy and what is going to be your final total energy. That's it. And what you try to figure out is just the change of the energy. This is the energy loss. You can think of it that way. This is the energy loss. It doesn't, I mean, the loss means the loss go in the form of heat to melt ice. All right. What is the total amount of energy initially, guys? Okay, well done. No problem. Its bullet is being shot right now. So it's going to be 1/2 mv squared. That's it. There's nothing else. Okay. And at the end, what about the final energy? Of course, it's going to be zero because there's no more speed in there. See, so back in the day of Newtonian physics, this is what you have to calculate. You're done with this. It's just like it's just 1/2 mv squared, and then you have the zero toward the end. But now we have a thermal aspect of the question here. You have initial temperature of 30 degrees Celsius because they assume that this is a large block of ice. So you assume that, I mean, you're not going to completely melt the block of ice over here. So that means you can expect that your final temperature of the bullet is going to be 0 degrees Celsius. You guys with me here? Okay, so that means you have the heat transfer due to thermal effect because the bullet has to cool down from 30 degrees Celsius down to 0. So actually there is a heat flowing out. So there is an extra heat loss. Or I mean, you can think of it like there is an energy flow, not only just the kinetic energy that gets reduced down to 0, but you have also the energy that gets transferred out. You guys with me here? All right, guys. So that's what it is. So you just have to take into account the delta E is the energy loss due to, let me put like the delta K. Yeah. That is the kinetic energy change. So let me put it here. This is the initial K. This is your final kinetic energy. And then what you have extra from that is the Q equal to MC delta T. Does that make sense?
Okay.
Yeah, because the bullet cooled down from 30 to 0. Okay, so what it means is, okay, let me write it down here. Let me write here. What about the heat flow? It's going to be M of the bullet, C lead, and the delta T of that lead bullets. All right, so let me put some numbers in here. So the bullet mass is 3 grams. I turned it into kilogram times negative 10 to the negative 3. C let you can look it up. Okay, some numbers. Delta T, here we go. Let me stick with the definition of the delta. It's going to be final minus initial. So it's going to be negative 30. You guys with me here? Is reduced. And that negative sign just indicating that the heat is being transferred out of the lead bullets. All right, so I just want you guys to start familiarize yourself with the sign. The negative sign means heat leaking out, it's flowing out, it's go out. Okay, so that means no doubt this heat is going to get you negative value because I mean the energy is dropped, right? It's get colder. Same thing over here. What about the kinetic energy change here? All right, so the delta E, which is delta K, is just going to be K final minus K initial. And that is going to be negative 1/2 mv squared. Of course, it has to be negative again because it's energy loss. Yeah, you're losing some energy. So they both they both give you negative numbers, no doubt. But that's it, guys. So you just take this number here, which, okay, I forgot to calculate. So it's going to be 1/2 negative mass of the bullets again, 3 times 10 to the negative 3, and the speed given to be 240 square. And then all you need to do is just take this number, add along with this number. They're both negative. That is fine. And then you just equate these two. Okay, let me write it whole thing here. Let me call this A and B then. I just don't want to, do the numbers. So these two numbers, A and B, added, even though they're both negative, but that's fine. You can put an absolute sign in here if you like. And then it's going to be equal to mass of the thing. This is what you want to calculate. So this is the ice that get melted and times L. So that means you should be able to calculate what is the amount of ice melt and you are done.
Okay.
Not bad, I hope. All right. So I think this is something that is very cool in the sense that if you ignore this Q altogether, your results will be completely, it's off by like almost like a factor of 2, pretty much, right? If you only take care of just the energy change. All right, so now you have to take into account the thermal aspect of the problem because now you know that there are temperature changes happening in your system as well. That's done for
Okay.
this topic right here. พอได้ not too bad, eh? All right, so I think this is sort of like draw the line, and we say this is complete the first part of this introduction between us, right? So kind of like, okay, get to know each other a little bit, get to know physics too a little bit, and then now we are going to dive a little bit deeper, guys. So we are done with the heat business over here. Let's bring up the next handout. All right, so you guys are supposed to download the handout in the number 2. All right, here we go. Now we're getting closer to thermodynamics, guys. All right, and it's gonna start to get a lot more fun. And I will give you a little bit of calculus with no extra charge here. It's coming. All right. So what we are going to learn today is now we talk briefly about work. They have the same aspect as heat in the sense that they both energy transfer. So what is work in thermodynamics term? We already knew is W equal to F dot S before, but we still use that here. We'll see. All right. And once we get that, we're going to get the link to the internal energy, the one that we discussed before, which is saying that is the total energy of the system. So instead of talking about like, hey, it's a total kinetic energy of the system average and all this stuff, we just call them easily, just say, hey, it's the internal energy, right? It's the total energy of the whole system. And once we get the connections between these two, actually these three, because we already learned about heat, about work, and about internal energy, and that's our time for the first law of thermodynamics. All right.
Okay.
Is that exciting? Okay. Well, Ajahn, you shouldn't be exciting anymore. You have been teaching this for many, many years. All right. I'm excited every time. Okay. All right, guys. So what about work? All right. I'm going to confuse you a little bit here, guys. All right. This slide is confusing. And it's supposed to be confusing because it's about the sign that I was talking about. There's a negative, there's positive. For the heat, there's in and out. But for work, there is stuff that you have to worry about a little bit. So stick with me here. I'm going to have to talk a lot about this slide over here. So let's start with this. Let's say you have substance. Actually, substance can be solid, liquid, or gas, doesn't matter. But we prefer to talk about gas in particular because we know the property of gas really well. Let's say is that you have a substance that can expand or contract. It does work on surroundings every time, but it expands. I don't know, this sentence ring sort of like resonates with whatever you're thinking here. When things expand, that thing actually perform work on the surrounding. On the other hand, if you have a compression of that substance, so it means the surrounding is performing work on it. Does that make sense? All right. So think about this one. Now, let's focus on this container a little bit. Let's say this is your system. Let's look at gas, all right, because gas is easy for us. So this is gas. You are given some maybe pressure, volume, whatever, cross section and everything perfectly fine. And then gas get compressed. So the volume reduced a little bit. So in this case, the force that actually pushing this gas down is going to be, of course, it's going to be external force. You guys with me? Okay. So this is external force compressing the gas down. So right now you can say that this force is doing work on to the gas. However, if you do things in a very equilibrium way, remember equilibrium in dynamics, right? It means like the total net force must be zero. So at the same time, actually, it turns out gas is actually doing the same amount of force in the opposite direction. It's like action, reaction, think of it that way. But because you try to keep things in equilibrium at all time, so whatever the amount of force from the external agent trying to do on the gas will pretty much do the same thing backward. No big deal. Okay, now one thing that you can see over here is now there are two forces. One is pointing down, one is pointing up, so they are pointing in the opposite direction. Cool. Now, I am asking you guys, hey, find me the work done by this external force. Let's focus on the external force first. But that can be done. Let me start up like, because you're working along the y-axis. So let me just, draw the xy axis just like what we had before. That's fine. And I know you guys remember we had the units vector. Along the x, you have the I hat. Along the y, you have the j hat before. All right. If you're not familiar with this for now, that is okay. What you're having right now is I would like to find the work done by the external force. By definition, it's just going to be force multiplied by the displacement in the direction of force, right? Cool. All right. So that is fine. So what you have right here is, because we're going to stick with these coordinates over here. So right now the force is pointing downward. So that's why I'm saying I have a negative F pointing down. It's mean that's the J hat is 4. And then your displacement, John, my displacement is this. I starting from here, I end up there. So if I write it on the same figure over here, this is your displacement, right? Okay, so you can say that your displacement vector, ds is a differential, yeah? So it's a differential of the displacement is going to be the dy j, or it's the dy pointing down, okay? All right, so this is what you have over here. But then, well, so what do you have? Well, wait a second over here. So what you have here, I think maybe it's my bad. I just realized that I think the sign over here is incorrect. What? Wait. A piston moved by dy, the work done on the substance. The work done on. Why the work done on? Whoa. All right. I think the figure is opposite. It's the expansion. Oh heck. I need to clap over here. Sorry guys. It's supposed to be like going from right to left, not left to right. Wait, but then you're doing the confusing over here. How did I use this slide before? Okay, I said I'm gonna make you confused. Now you're gonna get confused. It's because of my symbol over here. Oh my god, I just realized this. What? Negative F. Okay, it's the same directions. It's the work by the external force is positive. That is so weird. All right, guys, can you like forgive me for this? Can you just get rid of this first line? That's so bad. This is so bad. Oh my god. All right, guys. So forget about this line. All right, I'm just gonna explain to you right now. Oh, sorry. All right, I'm gonna explain to you right now without using any vector. You don't really need that one. Okay. All right, guys. So let's stick with this figure over here. So from now, from left to right, your external force is pointing down. Okay, right here. And your displacement is also pointing down. Okay, so right there. So that's your displacement vector. All right, so they're both pointing in the same direction. So what I can conclude is the work done by the external force is F dot with the displacement. Okay, they're pointing in the same direction. So it's going to be F dy cosine 0. Is it better? I think. Yeah.
Okay.
I don't know. All right, but anyway, so what you have over here is you're going to end up with a positive F dy. Cool. That's good. Now, if I'm asking you exactly the same question, but then what I'm going to ask you is, what about the work done by the system, which is the gas? What would be your answer? Because we already agree that we assume that the system is supposed to be in equilibrium at all time. That's the assumption that I'm going to elaborate later as well. But for now, let's take my word for it for now. That's if we assumed that the system is in equilibrium every time that we do the analysis. So it means the F the force that acting by the system. So let me put that subscript sys over here. So the work done by the system must be just opposite to the work done by the external force. You guys with me? So if I'm doing this, so it's going to be F of the system. But then, of course, your dy is pointing down while the force due to the system is pointing up. So F dot ds for the gas or for the system is going to be F dy cosine 180. You guys with me? So it's the same value, but negative. So what's my point? My point is, whatever you do, the external force will do the opposite work relative to the work done by the system all the time. There are two sides of the story. Okay. So if you focus on the system, and if the system do positive work, the work done by the external force will be negative. On the other hand, if the work done by the system is negative, it means the work done by the environment or by the external force must be positive. They're just opposite in sign. You guys with me? Okay, so that's why we're going to get down to the conclusion, and we're going to assume that we are going to focus on the system. Okay, one more time. All right, so I hope you guys okay with this explanation that I have here. Yeah, so far so good. All right, so now I'm going to stick with the system. Let's say the system is expanding. Expand, okay? So now you have to think backward a little bit. So it's mean right now the gas is going from right to left. It's expand, it's pushing the piston up. It's pushing this piston up. So how much work is the gas doing? Well, then, if you're looking for the gas right now, so the work done by the system is just on the expansion. So let's say expand. So the gas pushing the piston up. So it's going to be F pointing up. And now your dy is also point up. You guys with me? So now they are pointing in the same direction now. So it's going to be F dy cosine 0. Cool. So far so good. So now in the expansion process, the work done by the system is positive. But then we already discussed last time, force is something that we don't want to deal with anymore because, well, we're not doing Newtonian physics, and you don't want to deal with force in particular. We want to deal with something that is macroscopically measurable. So we go back to the definition of pressure. We saw before from fluid dynamics that the pressure is just force per unit area, right? When you measure it perpendicularly. So what that you can do is you can re-express your force in terms of the product between P and A. So I can put it to be P, A, and then you do dy. Cool? But then when you look at this, Wajan, if you look at this pair over here, A dy, A is just the cross-sectional area, the one that you got here. And the dy is just the height of this one. So actually, A dy is the volume that you get from your expansion. Is the change in the volume of this expansion. So that means you can wrap this in the box and put it as the P dV, the volume change of the system or the gas in this case. And that's how we're going to figure out the work done by the system. Cool?
Okay.
You love it. Why? Because here, pressure is easy to measure for gas. Here, volume is easy to measure. It's just the width, the height, or whatever the configuration that the geometry of that container have. That's fine. Okay, so that's the conclusion that I have. If you want to figure out the work done by the system, is PdV. But then, of course, you have dV over here. It's going to be like differential stuff. Things happens just a tiny, tiny, tiny stuff. So if you want the full value of the work done by the whole system, you just have to integrate them. So what you have to do is just add all the detail that you found for each change that is happening during that expansion process. Does that make sense? And that's it, guys.
Okay.
That's how you calculate the work done by the system. And now, if you really want to figure out the work done by the external force, what do? Just put a negative sign and you are done.
Okay.
Got that one? Yeah. I hope. So it turns out the business of finding the work done by the system is so easy. You are looking for the volume change. If the volume does not change, there's no work done. Okay. All right. Come again. That is the reason why, if you remember from chemistry, maybe the first diagram that you try to use to describe gas is the PV diagram. Even though you have other diagram, VT or PT, doesn't matter. But I think the most basic diagram that you use is PV diagram. And that's the reason why, because if you set P to be the vertical axis, V to be the horizontal X axis, can you sort of like see the utility of the PV diagram now? Here we go. P is Y axis, V is X axis. The integral of Y dx is just the area under the curve. So from now on, if you can explain the change of the gas using the PV diagram, for example, you might want to start from initial point, you want to go to the final point according to this process over here that you can draw on the PV diagram. And you want to calculate, what is the amount of work done during this process? All you have to do is just find the area under the curve. That is the W, and you are done.
Okay.
Isn't that cool? All right. And one thing that you can start to notice that you can start from the same initial points and you can end up at the same final point. But because you can connect these 2 points using any lines in the PV diagram, so that means you start from I, you end at F. They don't need to have the exact same amount of work done because the area under the curve, they are totally different. See that? For the second process here, the amount of work done is this area over here. For the third process there, the work done is the area under the curve here. So what I can conclude from here is the W is path dependent. Oh, that's too much. Dependent. Yeah. So before you can figure out the amount of work done, you have to tell me exactly how you change your system from I to F. Without the path, without those lines in the PV diagram, I'm not going to be able to tell you what is the amount of work done. Cool? That's one down.
Okay.
Let me ask you another question, guys. Among these three, do you think the work done is positive or negative? I don't need that, yeah? You guys still with me? It's so quiet here. So going from I to F, in these three, A, B, and C, do you think the work done by the system is positive or negative? Positive. Okay. Oh, thank you for participation. Perhaps positive. Okay, here we go, guys. Here, see, the definition is PDV. We said work done by the system is just PDV. We just look for the volume change. So if the gas expands, think of it, I am the gas. If I push the ceiling up, I am doing the work. I am the system. So in that case, if I notice that there is a volume increase, my work done must be positive. On the other hand, if I can notice that the volume is decreasing, the work done must be negative. Okay?
Okay.
And that's what this one for. See? Simple. You start from here. You end up there. Volume is less. You start from here. I mean, they're starting and ends at the same point. So, I mean, the volume is guaranteed to be smaller. So the answer for this one is W system is negative. Cool.
Okay.
Got that one? And of course, if they just, feel like, hey, I want to ask you something else, the work done by the external force is going to be positive in this case, in these three cases. Yeah. Start to get the feeling of what is about to happen here. All right. Keep going. If you still sort of confused a little bit here, try again, guys. So if you have a PV diagram And now, because we already discussed that it must be path dependent. So if you, for example, you start from point A, you end up at point B. And let's say you want to work along path number 1. So you really need to calculate the area under the curve. You're going from here, go to there, or I can call this point C. The amount of work done is just area under the curve. So it's just the width times the height. You guys with me? Okay, so if you know this level of the pressure, let me call this like P at A, and the volume, you can start at volume at A, and this is a volume at B. So change of the volume, you can see that now it's increases from A to B. It's expanding. So the delta V, here we go, is going to be delta V is just V final minus V initial, and it stays positive. So from A to C, you already got the rectangular area to be your work done. And now when you go from C down to B, there's no area under the curve. It's just a vertical line. So that's why you got 0 there. So your net work done from A to B following the path number 1 is just height times the width, and you are done. Simple enough. And it's automatically positive because the change of the volume is just V final minus V initial.
Okay.
Okay. If you want to compare this one to, let's say, path number 2, you want to go diagonally from A to B. What is the amount of work done? The work done is going to be area under the curve, highlighting in black over here. So it's a trapezoid area over here that you have to figure out. But it's still positive anyway, because the work done from the expansion must be positive. Right? What is the 0 again? The 0 is when you're going from C down to B segment here. This segment here, WC to B, has no work because there's no area under the curve. It's a vertical line. Cool? Alrighty. On the other hand, if you want to compare it, it looks dirty already. If you want to go from A to B, but following the third one, you can come down first. This one will have 0 work done as well. W from A, let me call this point D, is 0 because it's, again, vertical line. And then you go from D to B horizontally, it's going to be area under the curve here that you want. So let me do that green highlight down here. There you go. All right. I should use a highlighter better. It's still old style writing. Yeah. All right. But you got it, guys. Start off at least. Yeah. Even though you not totally understand 100%, but at least you get an idea of what it's about the work done and the PV diagram. Keep going. Here we go. Let's give it a shot. Okay. So an ideal gas undergoes a constant pressure expansion. So when you have a constant pressure expansion, think in your head as a PV diagram. Constant pressure, so it means pressure is fixed. So you think of horizontal line. Cool? All right. So now its initial pressure is 1 atm. So that's 1 atm. All right, unit is kind of bad. Its initial and final volume are given to be 2 and 4. Volume is here, 2 and 4. Yeah. Let's say everything is in cubic meter. All right, find the work done. So it means the work done that we're talking about is you start from here. Let me call it point, initial point. And then you do a horizontal line here because that's the constant pressure expansion to final point. See that? And then I can put an arrow here just to signify that it goes from I to F. Okay, what about the amount of work done, guys, here? W of the system is, let me write it as an integral sign first, P dV. But the pressure is constant. I can pull P out from the integral. The integral of dV is just V. And then I just put the V initial and V final there. So V initial and V final. So it's going to look like P times V final minus V initial. See? What does it look like? It's just the width times the height. It's the height times the width. Yeah, exactly just like what we agree is supposed to happen. It's just, it's going to be the rectangular area underneath that path right there. So I'm just use the calculus to confirm that, all right, it has to be area under the curve. And it's just going to be rectangular region for the constant pressure expansion here. Cool. But I just keep going. All right. Once I get there, pressure is 1 atm. You can turn it into Pascal by multiply by approximately like 10 to the fifth. Okay. So that's my conversion factor here. The final volume, whoa, 4. Initial volume, 2 cubic meter. And then see, the sign is automatically positive because the end point volume is larger than the initial point volume too. So it's automatically positive as we love it when we stick with the definition here. So at the end, what you get is just positive numbers here, which guarantee to be correspond to our understanding that gas is expanding. When they expand, the W by the system must be positive. You are done, guys.
Okay.
See how simple it is to calculate work done by the system. Okay. All right. Cool. So you understand this word automatically now. Find the work done by the gas. Our gas is our system right now. Cool. Try one more, shall we? All right. Then we take a break. Sounds like a good plan. Okay. เฮ้ยยังไหวกับอาจารย์อยู่ไหมโอเคฟิสิกส์ตอนเช้าๆน่าจะโอเคนะ Right. Don't forget to take some vitamin or something. 3 mole ideal gas. Oh, here we go. Undergoes a constant pressure expansion. We love it for now because we know constant pressure is just a simple horizontal line along the PV diagram here. The initial and final temperatures, are given to be 300K and 400K respectively. So now you are given the information about the temperature instead. Find the work done by the gas again. Shall we try it again here? So now you have PV diagram. It's constant pressure process somehow. So you can imagine it's supposed to be a horizontal line there. Okay. And now you given that 3 moles of gas. So that means you can write out N, small n, to be 3 mole. Cool. So what happened over here is, all right, Bajan, I'm going to start from point. You can use 1 or 2 or I and F, up to you. And let me change the mood here using point number 1. And you're going to expand horizontally because it's a constant pressure expansion to point number 2. Cool. There you go. Put an arrow there just to signify that it's expansion. All right. Oh, there's a question. Oh, go back a second. Oh, sorry. I just went too fast. Yeah. You want this one a little bit? All right. Just catch my breath a little bit here. All right. Very good. Is that my calculus writing bad? Have to go back and double check. Okay. Alrighty. All right. Sounds good. All right. Thank you. All right. Here we go. So what we have over here is exactly just like what we had in the previous problem. More than you just do exactly the same thing we just did. W of the system is the integral P dV. P is constant, everything can be pulled out. And the integral of dV is just V. And then you put the V initial to V final. Right now for this problem, we call it point number 1 and point number 2. So it's going to be P V2 minus V1, perfect. And it's just the width times the height again, if you can see from here. Okay, height is P and the width, delta P, V is just the width right there. Okay, cool. That's no big deal. But then we don't have the information about this P and the V, but that's all right because we are dealing with an ideal gas, guys. Is an ideal gas. So perfect. So you can say it's a P V2. They are the same P over here. You can call it P1 or P2. It doesn't matter. So it's a P2 V2 minus P1 V1. P2 and P1 are the same. And then now you use PV equal to nRT, guys. nRT2 minus nRT1. N and R are common factor. You can pull it out. N is 3. R, let me put just R there. So all you need is just the temperature difference, the change in temperature. Fine. It's getting hotter. You're going from 300K to 400K. So good thing is at the end, this difference give you positive number. 3R positive 100. You guys with me? It's 400 minus 300. Okay. So it's positive 100. Nice. Let me answer this. Positive 300R. You can substitute R whenever you like. But the final answer give you positive area under the curve. We love it. It's supposed to be positive because we know it's the expansion of the gas. So the work done by the gas must be positive as expected, and you are done.
Okay.
Yeah. Shall we take a break at this point? Yeah, but I think you see how can we calculate work done down to the final digits or whatever you want to do it. And you can now expect a little bit of calculus is coming after the break. Okay, guys? What is R? Okay, R is the gas constant. This is gas constant. So it's from PV equal to nRT. That's the same R. But I just don't want to substitute the value of that R. But if you want, you can substitute this to be like maybe 8.31 on and on. Yeah. And then you can do the calculation. At the end, you're going to get whatever final value in joules, if you like. Very good. Alrighty. All right, guys. So let's take 10 and then we'll see you after the break with more problems. Yeah.
Okay.
More problems. Physics problem. Before I forgot. All right, guys, try the next one, shall we? Okay.
Okay.
So let's determine the work done on a fluid that expands from I to F as indicated in the figure. Okay, so once again, we already knew that to figure out the work done, you need to have a path, right, defined somewhere. And I mean, the easiest way that we can describe the path is using PV diagram. Okay, guys, so let's attack part A first. Determine the work done on a fluid that expands from I to F. So what should it be? Simple, just area under the curve. Area under the curve. And you are done, guys. That's how easy it is for you to calculate.
Okay.
So all you need to do is just, okay, but you can split them, like, you know, whatever you want. Like you can do, or actually, you can just take the trapezoid right away if you like. Okay. There you go. So if you want, you can take this big chunk over here, right there, and then followed by that tiny bit of rectangle, and you're done. All right. And can you tell that, let's say, let me call this area A. Once you complete the whole thing is A. It's supposed to be positive A or negative A, guys? What do you think? The area under the curve is no big deal. Everyone can figure out the area. So should it be positive area? I mean, the positive of the numbers that you got from the area or negative numbers? What do you think? Ooh. Don't need that. I'm just having fun on my own here. All right. The answer is positive because it's expanding. See that? So part A, the answer is the work done by the, let me put like by the system for now, going from I to F is just positive A. Cool. All right. And because later on, we're not going to keep writing down the subscript system. It's just too cumbersome. So eventually, we're just going to call it W and be done with. All right. So from now on, we're pretty much going to assume that whenever you talk about the W, that means the W of the system. All right. And this is the part that maybe a couple of textbooks just use work done by the external in the formula. All right. But as long as you stick with the definition, stick with the understanding of everything, physics stays the same. It's just a matter of the preference that you want to talk about the W, that is the W by the system, or some textbook, they will refer to W as the work done by the external. Cool. Alrighty. But it seems to me, using the work done by the system seemed more natural somehow, because usually when we came, it's not like we came from Newtonian physics, we focus or our center of attention is our system, right? You're talking about the mass, and then we take mass to be our system. So same thing over here. It seems like if we try to learn thermodynamics from a gas system, then our gas system is supposed to be our system. So that's why I will try to use W that refer to the work done by the system to be our main focus here. Cool? All right, part B. What about how much work is performed on the fluid if it is compressed back from F to I along the same path? Whew, this is going to be good because the W over here going from F to I is going to be just the negative of that, part A. And you are done.
Okay.
Cool, guys? Because going from F to I, you're going to sort of like give exact same value of the area under the curve, but it's just the compression instead of expansion. So that's why you're supposed to get the final answer to be negative. Cool? All right, try again. I hope you understand a little bit better now of how to calculate the work done. One more. All right, guys, this is the challenge of the day. All right. Give it a shot, guys. A sample of ideal gas is expanded to twice its original volume of 1 cubic meter. Okay. In a quasi-static process. All right, I will come back and describe what does this word is sort of like, what does this mean? As shown in the PV diagram. So let's assume that you have a PV diagram with a curve, all right? The alpha is given. How much work is done on the expanding gas, guys? All right, guys, I want you to, try this one. I give you like 1 minute head start here. How can you figure out the work done by the gas from I to F? Yeah, from the look of it, it's just the area under the curve anyway, done. So there's nothing new here in terms of conceptual understanding. Is just there. It's still the area under the curve. And you can expect from the beginning that your final answer is supposed to give you a positive value. You guys with me?
Okay.
The reason is because you are expanding, the gas is expanding. So you're expecting that your final number is supposed to be positive. All right, but how much? All right, so for those of you that already written down, very good. So of course, the work done, which is now, this is a W by the system. I'm writing it a couple more times for you to familiar with this, can be found from integral of P dV. Cool. But now this line are given according to this function over here. So you can write down P as a function of V. So it's just going to be integral of alpha V squared dV from initial volume to final volume. Cool. All right, alpha is just a constant. I can pull it out. The integral of V squared is just V cubed over 3 from V initial to V final. Almost done. And then you just plug in the number. V final is 2. Okay, you can pull out 3 as well. So it's 2 cubed minus 1 cubed. This is in meter cubed. And that's it. As you can see, the numbers that you got from this integral is automatically positive. So you don't need to worry about anything in terms of like if you do it properly, you stick with the plan, you stick with the order that you're supposed to subtract numbers, your final answer is automatically have the correct sign for you. So it's going to be positive alpha over 3, and it's 8 minus 1 is 7. Is that right? Yeah. All right. And you can substitute alpha whenever you like, but at least that's the end of it. You're done. Cool.
Okay.
All right. That's the key. All right. And I just emphasize, I mean, not, it doesn't have to be emphasized, but it's just the way that they use the wording in the problem. This one, they say how much work is done on. See this? Can you see that? What we are calculating is the work done by the system. Done by the system. But they are just asking you to figure out the work done on. So actually this problem is trying to ask you to figure out the W external, guys. So the external work done is going to be negative of the W that we just learned or we just calculated. So your answer for this particular problem is supposed to be 7/3 alpha. And you're done. Cool?
Okay.
So I hope you see the contrast between if the problem asking you to figure out the work done by the system, that is your W system, or the problem asking you to figure out the work done on, so that is just the work done from the external force. But we already knew that these two are related to just the flipping of the sign, negative and positive. So that's easy to carry on your calculation using just the W of the system. Yeah. And then if the problem asking you the work done by, asking you to figure out the work done on, you just flip the sign and you're done. Okay. So that's why we stick with the definition of the W by the system. And then if you want W external, flip the sign. Any questions so far? Cool enough, I guess. All right. I thought this is like what? It's coming into the third year, right? We have been in COVID situation for full 2 years, and this one is like another quarter has already passed. So this is like another second quarter after 2 years. So it's been a long, long time. And I think maybe some of you guys are the students that sort of like have to do full online study all the time. I can't understand because I'm talking with the PC camera and then I'm kind of get sick a little bit here.
Okay.
No need to clap there. It's just like, all right. It's kind of missing something, right? Seeing face to face is way better. All right. But anyway, just my little complaints about the scenario. I hope it's not too long. We might be able to move everything on campus and bring normal things back to the way it's supposed to be. All right, guys, move on. All right, next. Now, we're going to have a lot of fun here, guys. Almost done. I think we got like 2 out of 3, right? We almost get all the components that we need to get to the first law of thermodynamics. And my goal is, I hope that today I'm going to be able to explain to you what is actually the first law of thermodynamics. All right. But before we get to that, I'm just going to confuse you a little bit more here, guys. But seems to me, I think this is very, very important example. And if you can understand this one, at least a little bit, you will understand why do we need thermodynamics at all. Here we go. So you have gas. Now imagine this one. You have to look carefully on this one here. All right. At least gas is admitted into a container that has a movable piston. So it means gas can expand, can be compressed and everything. So gas can change the volume. So that's good. Second thing is, look at the bottom of the container, guys. So the figure on the left showing the bottom of the tank connecting to a energy reservoir. But if you compare this to the right side of this setting, you can see that the gas on the right figure is being concealed, or is being sort of like put in some insulations or something that you don't have any connecting part to the outside world. You see the difference here? So the left, the gas sort of like do some connection to something else that has some, I'm going to explain about what does it mean by energy reservoir, but at least the gas has some way that can interact with the environment somehow. But on the right, it seems like gas, it's pretty much like, being isolated from the whole universe. It's being insulated. Okay, so there's nothing supposed to exchange whatsoever. So the idea of the figure on the left, the energy reservoir, see this, they say at temperature. So when they say at some temperature, it's the same thing as right now, you are sitting in a room. And right now, your environment or whatever your air around you is a huge, huge system. You can imagine that this is the air of like maybe Bangkok area, for example, or maybe Salaya campus, for example. For you, that's located inside the Salaya air. My question is, can you warm that air a little bit? If you say, hey, it's getting, a little bit too cold, I want to warm the air up by rub your hand. You guys know, like when you rub your hands get warmer a little bit, right? But you know, the amount of energy that you created, amount of heat that you generated in the palm of your hands won't change the temperature of the whole Salaya's air, whatever, right? That's not possible, right? That is because the amount of total energy of the air around Salaya's campus is huge. So that's why we call this huge amount of energy is called energy reservoir. And because we already learned about the connection between the energy and the temperature, so it makes no surprises that it's supposed to be at some fixed temperature. So that's why they say energy reservoir at fixed value of T, because you cannot change it easily, right? You can turn on your computer, you can, turn on the heater or whatever. You're not going to be able to warm up the whole Salaya's campus temperature. That's not possible. All right. You need way bigger system to do this kind of thing. So this figure is trying to tell you is that gas is connected to this energy reservoir at temperature Ti. So eventually, because we already learned that they are in thermal contact, so eventually they are going to be in equilibrium. So this is the reason why gas is supposed to have the same temperature. And this temperature is going to be fixed because it has to be the same temperature as the energy reservoir. For, let's say, if somehow gas get a little bit hotter, by thermal contact, there will be heat leaving to the energy reservoir. Or if the gas somehow get cooler than the reservoir temperature, there will be heat flow in to compensate that. And eventually gas and the energy reservoir will stay at the same temperature. If it does that, then we do. All right. So we're not going to be able to do that, right? So what you have over here is energy reservoir. So, okay, once again, if you want to imagine this in a mechanical way, you think of it like a water reservoir. You're going to water reservoir. And then if you want to steal a bucket of water from the reservoir, you're not going to change the level of the water in that dam or in that reservoir. Does that make sense? Or if you want to dump some water into the reservoir, I mean, you're not going to change the water level. Impossible. Same thing over here, right? But we talk in the aspects of energy, right? And then when you have a huge amount of energy, you're going to rub your hand and warm up. No, you're not going to be able to do it because the amount of energy is just so tiny. Or you're going to steal energy a little bit from your environment. It doesn't change anything. All right. So that's what it is. Now, what happened when, here we go. We already learned about the gas expansion, right? So here comes my question. Let's say that now you are looking at the situation where the gas is expanding. All right. Even though you have your hands on it, that's fine. All right. You might place it. You don't need to pull it up. Let's say it's if you want to do it, you can pull the gas. You can pull the piston up. Okay. Or, you can say that the gas is pushing your hands up. Doesn't matter. It depends on the perspective of things. But the idea is, let's say the process that you are considering is gas expansion process. So gas is expanding. So your hands that you handle, that you place on the handle can feel that the gas pushing your hands up. Okay, it's pushing your hands up. My question is, what happens? The question is so broad. What happened? Of course, my question is, what happened to the work done by the gas? What about the work done by the gas? So you say, Jan, gas is expanding. So that means the work done by the gas is supposed to be positive. See, gas does work. Cool? I think this is the key question. What about heat? Well, Ajahn, just read your handouts. No. I just want to test your understanding first. What should happen to the heat flow? We're going to spend a lot of time understanding this here. I need it from you. What should happen to the heat flow? Gas expands, it performs work, no problem. Gas is fixed in temperature because of the connections or thermal contact with the energy reservoir, no problem. Now here comes the question. What should happen to the heat transfer? Should there be any heat transfer? Even though the slides already suggesting that it's supposed to have the heat added, but do you get why? Okay, here's the explanation, guys. Imagine this. Remember, we already emphasized that temperature means energy, or let me put it like a total kinetic energy of the system. Make sense? Temperature is telling you the total energy in your system. And we said, if your system does not change in energy, it means your temperature will not change either. So what you have right here is temperature is fixed. So it's in the indication saying that your energy, gas energy does not change.
Okay.
But then gas do some work. How can it be? Imagine this. I am the gas. All right. I have some energy in me. I already ate some breakfast and everything, so I have some energy. Let's say I push the ceiling of my room up. I'm doing some work, right? I'm doing some work here. So the way that I'm doing it, if I don't have any other source of energy or anything, I have to spend my energy to do that work. I have to push up, right? So I have to, burn some food and all this stuff, turn it with the ATP and all this stuff, flex my muscle and then push it up, right? So I have to spend my energy to do the work. But look at this scenario over here. Oh, hey, Dan, wait. The condition here is you're not supposed to change your energy. Whoa. What does it mean? It means, hey, Dan, you cannot burn your food that you already ate, but you still have to push up your ceiling. How could that be? I have to maintain my body energy. I cannot spend my energy. The only way that I can do is I have to steal some energy from the reservoir. So that's why there is the heat flow in. And the amount of heat flow in had to be perfectly compensated for the work that I am doing. You guys with me? So I have to steal some energy from somewhere else, and that will perfectly match with the amount of work that I'm doing, so I don't have to spend my own energy. Cool. You see what I'm saying here?
Okay.
And that is thermodynamics. It's trying to link between two means of energy transfer, work and heat. See? So these are the two that's describing the energy transfer. And thermodynamics added the dimension of, use dimension, add the aspect of thermal possibility. Back in the day of Newtonian, you only do work, push, pull, drag, whatever, you just use forces. But now you have thermal aspect to it. Okay, so this process gives you the idea of the relationship between the work, the heat, and the energy of the system. Wow. Got that one? Try again. Look at this one, guys. Now you have almost the same amount of, let's say it's same amount of gas, same volume in the container. But then right now you have insulating wall. So you insulated everything. So by insulating everything, so it means you don't allow heat to come in or out. So heat, definitely no flow. There's no heat flow whatsoever. Okay. But let's say that initially the gas is being contained in the bottom half of the container with a membrane, but somehow membrane just breaks. Bam. So gas will fill up the whole space. No problem. So in this free sort of like expansion inside the container, does gas perform any work? What do you think? This weird sound effect. Does it do any work by this expansion? But it looked like it because initially you might have like VI, but then at the end you increase the volume to twice as big, right? So there's a volume increase just like you told me. So it's supposed to do positive work. The answer is no. Wait. You cannot tell that the gas is expanding because by looking at the wall of the container. The wall of the container doesn't expand. You got what I'm saying over here? There's no expansion of the gas because your container doesn't really expand anything. I am not pushing up the ceiling. The container doesn't get, bloated or anything. No, nothing. So what I'm saying is if I put my hands here, that's my ugly hand there, you're not going to feel any push from your gas. Nothing. So that's why no work. So here comes no work, no heat. The energy will not change because you don't have any energy transfer. So in this case, the temperature is also fixed. See? So these two have the same features of no temperature change. So it means these two scenarios give you constant energy of the system before and after. However, on the left, whoa, you go crazy with the work done by the gas along with the heat flow in, blah, blah, blah. But on the right, 0 for both work done and heat. You see where I'm going at here right now? So this is what I'm trying to get to is work and heat cannot be used as state variables. You guys remember state variable, right? The P, the V, the temperature, PV and T are state variable. The reason is because when you come into this room, I can make a measurement of temperature of this room and then you're done. All right, let's say like 30 degrees Celsius. Okay, fine, done. I don't have to tell you what happened to this room 2 days ago or 2 minutes ago or 2 hours ago. The temperature is there. I can come in here. I can make a measurement of pressure. It could be like 1 atm. I don't have to look at the history of the pressure of this room. It's 1 atm. Cool? All right. Volume, same thing. But then if I say, well, Ajahn, what about work? If let's say the system perform work of 100 joule, can you tell what happened to the system? No way that you can tell because there's so many ways that you can do with the system to make the work done equal to 100 joule. You see what I'm saying over here now? See? Example, what about heat, Ajahn? Let's say if you transfer heat 100 joule, there's so crazy unlimited numbers of ways that you can transfer 100 joules of heat because you might transfer in 200 and transfer out 100 and then you're left with 100, or somebody can transfer in a million and transfer out like 99 9 or whatever thousand and then you're left with 100. Possible. Nobody knows. So that's why the W and Q, you need to tell exactly what you did with the system. So that's why the work done we already saw from this calculation, you always need to attach with somehow PV diagram. It's path dependent. Same thing with the Q. Q is also path dependent, even though you don't have PV diagram per se, but it's just saying that you have to tell exactly what do you do with the heat. Did you put in how much? Did you put out how much? Just for you to be able to calculate the total amount of heat flow. Okay? So in conclusion, W and Q, you need to tell exactly what happens, except one, the energy of the system. You don't need to because it's going to be the same as what you saw before. Kinetic energy is 1/2 mv squared. So as long as you know the speed of the mass, you don't have to know the history of this mass. You plug into this equation, you're done. You can calculate the energy right away. And we already knew that the total kinetic energy of the system, we're just going to call them collectively to be internal energy. So the internal energy is a state variable. Woo! Isn't that cool? All right.
Okay.
And we love state variables because you don't need history. Just like MGH over here. If I put it here, let's say this is my floor level, potential energy is 0. I place it up here, it's MGH. You don't have to know the history. It's MGH no matter what. You can move things around. I can move up like this straight. I can move up diagonally. I can throw this mouse to you. You throw it back to me and put it in there. Well, they're all MGH. Doesn't matter. So that's why we love the concepts of energy before back in the Newtonian physics day, because energy is path independent and can be used as state variable. It can tell the state of the system. Isn't that cool?
Okay.
So I hope you sort of understand the behind the scene, intention of physicists back in history day. They already put a lot of thought into this, why they come up with the concepts of energy and on and on. All right, so back to our business over here. So in conclusion, internal energy will be path independent and can be a state variable. Now, because we already said we're going to focus on monatomic ideal gas, that's a nice thing about it is because the total kinetic energy of ideal gas can be written down perfectly with the following equation right here. Isn't that nice? So the form looks almost just like PV equal to nRT, except you have an extra factor in the front, 3/2 nRT. That is the total translational because that's the only way that monatomic gas can do 1/2 mv square. That's n times 1/2 mv square can be written in terms of, see, isn't that surprising? It depends only on temperature, guys.
Okay.
And that's perfect. We already saw it. We love that concept. We knew that concept, that energy links to the energy of the system. Bam. That's it. All right. And now it's your preference. You want to use the small n, you use small nRT, and then small nRT is perfectly equal to the capital NKT. So you just need a factor of 3/2 in the front. You will be able to calculate the internal energy of that monatomic ideal gas, guys. Oh, cool.
Okay.
All right. So that's give you another equations. And here comes the first law of thermodynamics, guys. Here you go. All right. So a lot of talking today. All right. But I promise next time there'll be a lot of calculations. All right. Along with the calculus. Okay. So here is the conclusion. From now on, you will have 3 terms in your first law of thermodynamics. First, of course, heat. Second, W. And the third, now, internal energy. But wait for it. The internal energy is the energy contained in the body. But the Q and W, a signifying transfer. I cannot emphasize enough. Q and W means transfer. There must be some flow. There must be some change. There must be some transfer, right? There must be some there must be some transaction going on. So that's why you're not going to equate this to U. You're going to equate this to change of the internal energy U. So that's why the delta U is supposed to link to the W and Q. Cool?
Okay.
But how are they linked? Here we go. Conclusion is right here, guys. This figure right now. You have a system. Now we agree with the sign. If heat flow in, you have positive heat. If heat flow out, you have negative heat, right? But imagine this. Heat flow into the system. What should happen to the energies of the system? Increase. So that means positive Q linked to positive change of the internal energy. Make sense? And negative heat means it leads to negative change of the energy. So that's why the delta U and Q supposed to go hand in hand, same sign. If Q is positive, that should give a positive delta U. But that's not the end of the story. You have to take care of the W, the work done by the system. So now we already agree that the work done by the system is positive. But then when you have a positive work done by the system, what should happen to this energy of the system, guys? Just like my example, if I perform work, my energy is supposed to drop. So that means positive work done by the system lead to the negative change in the internal energy. Does that make sense? And vice versa, if there is the negative work done by the system, which means there's some work done on. So that will lead you to positive change in the U. So what I'm saying over here is the W of the system will have a negative impact onto the change of the U. If the system perform positive work, it will give the negative impact to the U. And that's why I have to add the negative sign in front of the W here. And that's our first law of thermodynamics. Isn't that easy? So all in all, the first law of thermodynamics is just conservation of energy, but it's been generalized to include the thermal effect. Let's say if you get rid of this, you don't care about the heat, delta U equal to minus W, that is perfectly conservation of energy that you saw before. And because back in the day, you talk about the work done by the external force. So that's why in Newtonian day, delta U equal to W external. That is just conservation of energy, yeah?
Okay.
Got that one? All right, so conclusion is thermodynamics is just conservation. First law of thermodynamics is just conservation of energy, but it's just including the thermal aspect of the system. Cool. But then there is confusion happens in some textbook. They do not write this first law in this form. It shows up here as a positive sign. Can you guess what happened in that textbook? Very good. Whatever you're thinking is correct. So in that textbook, this W just mean W external. That's it.
Okay.
So what I'm saying over here is once you understand the fundamental of all of these terminologies over here, whatever form that you are going to look at, it doesn't really matter. Okay. You're going to look the same because here we go. I'm going to sort of like settle this thing down just like once and for all. If I write this first law in this form, delta U equal to Q, this is no ambiguity. The Q is always defined this way. Positive Q means heat flow in, negative Q means heat flow out. So they have the same direction as the delta U. There's no problem. And then instead of confusing you with the W positive, W negative, doesn't matter. If I turn this W into P dV integral. Oh, how come I cannot draw here? And that's it.
Okay.
This will definitely be exactly the same in all textbooks because in our case, we call this PdVW, okay? Because this is our W system. But in other textbook, they just call this whole negative PdV to be W, and they just define it as external. See, you are done.
Okay.
Right. So no matter which kind of textbook that you're dealing with, as long as you express the work done as an integral of PdV, you will end up with the same equation over here. It's just a matter of which part of this expression you're going to call W. Okay. For us, it seems to me, just take PdV integral to be W. That seems to work for me. And then you leave negative sign in the front. Okay. However, of course, in the textbook, even our reference text, they actually use the positive W. And it's unfortunate, but I found out that I taught this one many, many years back then, and then I following the textbook. And then it seems like you guys made a lot of mistakes in terms of the sign. So that's why I sort of like caught the idea that it seems like by following the W to be the W external, it seems like you have to flip the sign in your head all the time. So I decided to switch all the sign and then just define W to be W system from that day on, maybe, I don't know, 5 years ago. All right. So maybe when you look at the answers or, some solution that I provided in the homework set, maybe the solution still in the Q plus W, but I hope by understanding what the W means here and what the W means in the textbook, you shouldn't have any problems in the future, I hope. Okay. All right. But if you have, then we can discuss later. All right. But for now, this is the first law of thermodynamics, guys. Here we go.
Okay.
All right. I know I talk a lot today, and all right, we're gonna sort of like cool down and then toward the end of the lecture here by just, give you just, let's do two more problems and then be done. Just, do some, quick question over here. Just have you think about it. The drawing shows a pressure volume graph, PV diagram, in which a gas expands at constant pressure from A to B. Cool. And then go from B to C at constant volume. Fine. Complete the sign in the table below, shall we? All right, having fun, yeah? Woo. No need. All right, guys, from A to B. Which one is the easiest for you to spot? Yeah, A to B. Volume increases, so gas expanded. So at least W must be positive for sure. Okay, and W, don't forget, is a W system. Okay, that's we're gonna stick with this notation over here. And then now from first law of thermodynamics, change of the internal energy is Q minus W, because they already said that delta U is positive. Okay, let me move things around here. So Q is just delta U plus W. So from here, because the delta U is already positive, W is also positive. So it's guaranteed that Q must be positive here, and you're done.
Okay.
See, simple. Try going to B to C. That's even easier because B to C, W is 0. Cool. And if they already given you that for part B, so it's not part B or part A, it's A to B, sorry. From A to B. And from B to C, W is 0. So from the first law of thermodynamics, delta U equal to Q minus W. W is gone. Q is positive, so delta U must be positive along with it. And you are done.
Okay.
All right, still okay. Well, that is not bad. That's not bad. All right, but of course, this is not going to happen in the exam. All right, but anyway, we need some basic like this first. Okay, last one, guys, for the day. All right, Labor Day's extra problems here. The drawing shows a pressure versus volume plots for a 3-step process. Determine the sign for delta U, Q, and W during changes from A to B, B to C, and C to A. Now, this one is harder now because there's no predefined positive, negative sign for some of the quantities in the first law expression. You just have to figure out by your own for all of them. All right, so let's give it a shot here. So we have A to B. So let me draw a table just like what you saw before. And then you have delta U, you have Q, you have W. Sounds all of that. Okay, guys, help me here. A to B. You guys still with me? Yeah. It seems like number of students getting lower and lower. Okay. All right. Attack the easiest one first. W. Yeah, W is good because from A to B, you can see is definitely expansion. Yeah, expanding gas give you positive work done by the gas. Now the other two, which one is easier to spot the sign? A to B. Wow, well done. Definitely heat is tough. Heat seems to be the toughest, the Q, because there's no formula, there's nothing. Delta U still have some formula. U is 3/2 in RT. You just saw that. So it seems like U seems to be better. But how can we tell that A to B is going in a positive change of U or negative change of U? Here we go, guys. Just one last tip of the day. See PV equal to nRT equation. That's equation of states for either gas. If I write it now here, P, V, P is Y, V is X. Look on the right side. If I fix the temperature, then the right-hand side will be totally just a constant number. With me? Once temperature is fixed, the right-hand side is just a constant. So it's a constant. You remember this equation here? X, Y equal to constant. What is the shape of this? Very good. Very good. Whatever you're thinking is correct. X, Y equal to C. And actually they are both sides of this one, but because we don't care about the negative value. So it's just it's called, I think it's called, I don't know, orthogonal hyperbolic or whatever. It's a hyperbolic that's shift or rotated 45 degrees. So the idea is xy equal to constant is just the curve that's saying that the product between x and y has to be fixed. So if x is big, y must be small. If y is big, x must be small. So it's a curve like this. With me? I draw the one that's passing to B. That. So every time that you pick one value of t, you will get one curve of this one. So it means there will be tons of this curve, depends on the constant here, but they all look the same. They will all look just like a curve like this. So what I'm saying over here is every time that you are looking at a PV diagram, you should be able to just imagine this line in your imagination all the time. By knowing this, you also know that the temperature is going to be high when the lie is higher lying, right? The higher lying curve means higher temperature because that's the only thing that's going to sort of like show up on the right hand side. So this is going to be low. Why do I love the temperature? Because we already learned that higher temperature means higher energy. So going from A to B, can you answer me now? What is going to be the change in the U? You jump from a lower lying temperature to a higher lying temperature. You increase in temperature. Temperature increase, delta U increase along with it. You are done. Cool?
Okay.
And then once you figure out these two, Q will follow from delta U equal to Q minus W. So Q is delta U plus W. So both are positive. So Q must be positive as well. And you're done.
Okay.
Cool. Try again. B to C. Going from B to C, you jumping from B down. See that? You're going from higher lying to a lower lying curve. So it means you jump down in temperature. So delta U must be negative. Nice. However, you are still expanding. You're going from B to C, you're still expanding. So the W must be positive. And from that, well, Ajahn, delta U is positive, W is negative. Then you probably don't know for sure because it depends on the value. They could be perfectly cancel or they could be positive, negative. Let's say don't know at this point until we know more. Okay. But yeah, all right. And the last one, let's go back from C to A. So you want to go from C back to A over here. First thing first, you jump down from higher lying curve to a lower lying curve. So delta U is supposed to be negative here. Cool. And then W is also negative because now from C back to A is a compression process. Volume decreases. So now when you have both terms negative, so it's guaranteed that Q has to be negative as well. And you are done.
Okay.
Cool. All right, guys. So I think this is a, sort of like now ease you guys into the first law of thermodynamics. On Wednesday, we're going to do a deep dive and then not only the sign that we have to fill up, we are going to do full calculations for all terms and things start to get crazy on Wednesday. Sounds like fun? All right. If that is the case, that is it today, guys. And I will see you guys on Wednesday. Have a good day.
Okay.
Bye-bye.